Before you and I dive into the details of subnetting, there is one thing that we need to make sure that we understand and comfortable doing, and that is the conversion from binary to decimal and from decimal to binary. See if you master this skill, subnetting becomes a piece of cake. So it's worth to briefly go through one of the techniques that can simplify this process. And I said one of the techniques because there are plenty, and the best one of them is whatever you're comfortable with. Okay, as you can see, I just drew a table here with the power of 2's in the top row. That will help us do binary/decimal two-way conversion. I suggest that you pause this video and go grab pen and paper, draw one like it, because you and I will be going through some examples. In every scenario that requires subnetting, there are 4 key elements that we need to identify. Those elements are the initial network address, the initial subnet mask, either in CIDR format or decimal format, the number of subnets we need, and the number of hosts per subnet. Most of the time, the initial network address is pretty much straightforward. The number of hosts per subnet is also straightforward, but they might try and confuse you by saying that we need a certain number of hosts today, but it will grow to a larger number in the future. In this case, you'll need to cater for the larger number. The confusion starts with the initial subnet mask, because you and I have been taught that there is a default mask depending on the class that the network address belongs to, which is kind of true. However, sometimes you get presented with a network address and a mask that is not the default mask. For example, 11.0.0.0/16. And you'll think, oh, this is not the correct mask because 11 is class A and class A is /8. Well, the rule isn't that rigid since VLSM, meaning that it is allowed to have any mask that suits your needs. So let's have a generic example to clarify a bit all of this stuff that I've just said. Let's say that we've been asked to use the address a.a.a.a to run a network composed of b number of subnets, where the first subnet, let's call it subnet 1, has x hosts, the second subnet has y hosts, and the third subnet has z hosts, or z if you're from the States. And the rest up to B are serial links, and we know that serial links require 2 addresses. So far, we've identified 3 of our key elements. What we need to do next is figure out the initial mask. If they specifically told us the mask that we are going to start with, that means we're all set and we can move to the next stage. If they didn't, that means we are going to use the default mask. The way to figure out the default mask is by looking at the first octet, or byte, or what you might call it, and that will tell you the class of the network address, hence the default mask. Now if you don't know what I mean by classes or the default mask, just bear with me, I will clarify in a minute. Let's take the address of, let's say, 113.0.0.0 to practice on. It is unlikely that you will get such an address, but let's just use it for the sake of learning. So, what class is this address? To find out, we can look at what range 113 addresses falls into, and that would be class A. Therefore, the mask is /8, or 255.0.0.0. Let's say that you got this on an exam, and you forgot the range, and you can't check your notes. You'd still be able to figure it out and save the day. Let me show you how. What you need to do is convert the first octet to binary. In our case is 113. An octet is 8 bits, so we will be using the 8 left columns of our table. It is good to remember that all class A addresses starts with a 0, and class B starts with 10, and class C starts with 110. The way I remember it is that I imagine the 0 moves to the left, flipping its path to ones. So let's start converting the first octet to binary. In my case it's 113. And by the way, you can choose any address you want. You can still follow the same steps. I'll walk you through how I used to do it when I first started learning this stuff. I first ask myself, what is the largest power of 2 that is included in the number that I'm trying to convert? In my case, it's 113. Is it 128? Nope, because 128 is larger than 113. That means I'll put 0 under 128. Is it 64? Yes. So I write 1 under 64 and I do 113 minus 64 because we've accounted for it, and I repeat the process for whatever is left until I account for the whole number and reach 0. In my case, 113 minus 64 is 49, not yet 0, so I'll have to repeat the process on 49. And by the way, if you're working on a different number, you can work on your results. In my case, I have to repeat the process on 49. Is 32 included? Yes. We put 1 under 32. 49 minus 32, that will be 17. Is 16 included? Yes. 1 under 16. 17 minus 16, that will leave us with 1. Is 8 included? No. So I put 0 under 8. Now I know that the last bit is 1. So I don't have to repeat the process for 4 and 2. We can go ahead and put 1 in the 1 column. 1 minus 1 is 0, which means we're done, and we fill the rest with zeros. So 113 is 0, 1, 1, 1, 0, 0, 1 in binary. And because we forgot the range of classes, now we can see that it starts with a 0, making it class A. Therefore, the default mask is 255.0.0.0, which is the same as /8. And we save the day. Oh, by the way, if you're not sure why 255.0.0 is the same as /8, not to worry, I will quickly explain it. You see, the mask has the same format as an IP address, which is 32 bits, where every 8 bits are separated with a dot and converted to decimal. Let's do that using our magic table. So, here is our magic table. The first octet is 128 plus it's 172. Let's fill up all the binary values on the table. So 172 dot 168, 8 plus 2 is 10. Oops, it's 1, 1, not 0, 0. 2 plus 1 is 3, and boom, 172.168.10.3. Okay. Usually the mask address has a bunch of ones beginning on the right side of it, which maps to the IP address. We identify the network portion of it. And slash, let's say X, or whatever number, is called CIDR notation, as I mentioned in the beginning. That number represents how many ones are there on the mask address. Whatever X is, you pick a number. I pick /17. Odd, I know. That means there are 17 ones on the mask, and the rest is 0. It is important to remember that there is no 0 in between these ones. After converting into decimal, let's separate the octets. It is important to know that it's only 8 octets at the time. So the first octet will give us 128 plus 64 plus 32 plus 16 plus 8 plus 4 plus 2 plus 1. That will be 255. The second octet is the same, so it will be 255 as well. The third octet has only 1 in the beginning, and that falls in the 128 column, so it's 128. And the last one is just a big fat 0. So I'll get 255.255, then 128.0. And that's it. You can practice on your own random numbers if you're still unsure. Okay, back to our example. Let's clear this up a bit. So far we have two of our key elements, the network address and the subnet mask. Now we need to know the number of subnets and the number of hosts per subnet. Well, that depends on how the scenario is presented to us. It could be a topology like this, where you have to count the number of networks, or more specifically, the broadcast domains. In this case we have 1, 2, 3, 4, and 2 VLANs, making it 6 subnets. Or you might get a paragraph describing the network. It might say something like blah blah blah, branch A needs 500 machines, branch B 100 machines, branch C has a total of 1500. Half of it for VLAN 1 and the other half is for VLAN 200. Something like this. Okay then, let's start filling up the rest of our key elements. Again, you can use your own scenarios. I'll be using the topology one for now. So this one shows that we need 6 subnets. Let's associate subnet 1 with branch A, so on and so forth. So branch 1 needs 500, or subnet 1 needs 500, subnet 2 needs 100, subnet 3 for VLAN 100 needs 750, and subnet 4 for VLAN 200 also needs 750. Anything else? Yes, the serial links. Subnet 5 needs 2, subnet 6 needs 2 as well. Those are serial links. Now we've completed the 4 key elements, which means we can proceed to the next step. The next step will be to get this number of subnets that we need. In my case it's 6 subnets out of this IP address. In my case it's 113.0.0/8. How are we going to do that? First we need to figure out how many bits that are needed to represent this number. If we're not sure straight away, we can convert it to binary and find out. To me, I can see that 6 fits in between 8 and 4, which means 3 bits. But let's just do it in a methodical way. 32, no, 0 in here, 16, same, 8, same. Is 4 in there? Yes. So 1 in the 4 column, 6 minus 4 is 2. Not yet 0, so we'll repeat the process on the result, which is 2. 2 is in the 2 column, so 1 in here, 2 minus 2 is 0. Therefore, there are no numbers left to account for, which means we fill the rest with zeros. You know that the zeros on the right side of a number don't matter? For example, let's take 25. 25 is the same as 0025, but it's not the same as 2500, especially if you're talking about money. The same thing applies in binary. Consecutive zeros on the right side of a number don't matter. So 6 needs 3 bits. To find out how many combinations we can do with 3 bits, we do 2 to the power of 3, which is 8. The first one is 000, and the last one is 111, which we can insert into our initial IP address. So it will be enough to satisfy our requirements. We didn't use 2 bits because it will give us only 4 combinations, which is not enough. Makes sense, right? What about 4 bits? With 4 bits, we can have 2 to the power of 4, which is 16. So we can have 16 combinations, starting from 0000 and ending with 1111. And we can use the first 6 and have 10 left over. Why don't we use 4 bits instead? We wouldn't want to do that because 10 leftover subnets will be unused and wasted. And we need to preserve IP addresses as much as we can, because today almost everything needs an IP address. Printers, TVs, watches, air conditioner, a coffee machine. Hell, I've seen a bathtub that needs an IP address. Anyway, 3 is the choice that makes sense in my scenario. So let's start making those subnets.